Today we are going to explore complex zero and the fundamental theorem of algebra. Here is a picture of the breakdown of the complex numbers. Let's turn to some definitions that we're going to use in this section. Conjugate. The conjugate of a complex number is the opposite of the imaginary part. Theorem. A general proposition not self-evident but proved by a chain of reasoning. A truth established by means of accepted truths. A corollary. A proposition that follows from and is often amended to one already proved. Irreducible quadratic. A quadratic polynomial that cannot be factored by rational numbers. A lot of times before, when you were factoring, you would write something like prime polynomial when you would try to factor it because it wasn't factorable. That's what we call an irreducible quadratic. The fundamental theorem of algebra. A polynomial, this is our polynomial that's given, with degree n greater than or equal to 1 and with coefficients that may be real or complex, have a factor of the form x minus r, where r may be real or complex. In other words, polynomials with coefficients real or complex can be factored completely into real factors and irreducible quadratics. The theorem also gives the number of solutions to the polynomial equation. If f of x is a polynomial of degree n, then f of x has exactly n roots, counting complex numbers and multiple roots. The conjugate pair theorem. If a polynomial has real coefficients, then any complex zero will occur in conjugate pairs. That is, if a plus b is a zero, so must a minus bi be a zero. Corollary. If a polynomial has an odd degree, then 1 0 must be real. For this corollary, we understand that because our n behaviors, when it's an odd, have opposite n behaviors. So at one point, this graph is going to cross the x-axis somewhere, whether it's positive or it's negative. It's going to cross the x-axis somewhere. How to find the remaining zeros of a function? How many zeros does the function have? For every given imaginary, there is a conjugate. Let's look at some examples. Information is given about a polynomial f of x whose coefficients are real numbers. Find the remaining zeros of f. Number 1 has a degree of 3. So 1 0 is 5. My second 0 is 4 minus I. So my remaining 0 is my conjugate of 4 minus I. So I have 4 plus I. There's my conjugate of that complex number. Number 2, degree 4. 0's 2 minus 5i. There's one complex number, so that means 2 plus 5i is another 0. So that's my second 0. Then my third 0 is I have 8i, which means I have negative 8i as my fourth. Next, we're going to look at forming polynomial functions given some zeros. First, look at the given degree. List the given zeros. What zeros are missing? Set up x equals with each factor. Then set each factor equal to 0. Multiply all the factors together. Number 3. Form a polynomial f of x with real coefficients having the given degree and zeros. So it has degree 3, so that means I have 3 zeros. My zeros are 1 plus I and negative 8 that are given. Since my first one is complex, I know if I have 1 plus I also must have 1 minus I, and then I have 8. So there are all 3 of my zeros. Now I'm going to take each factor. They're solved, right? So I know that x is equal to 1 plus I. I also know that x is equal to 1 minus I. And I also know that x is equal to, that should be negative 8. Negative 8. Now I'm going to set each one of these factors equal to 0. So I would subtract 1 minus I from both sides. So I get x minus 1 minus I equals 0. Do the same thing with the next one. X minus 1 plus I equals 0. Do that with the last one. Add 8 to both sides. So I have x plus 8 equals 0. Here are my 3 factors. Now I'm going to multiply them together. So I have f of x is equal to x minus 1 minus I times x minus 1 plus I times x plus 8. When I have these conjugate pairs, I set them up so that I'm really looking at multiplying difference of squares. So here I'm going to have x minus 1 squared, then minus I squared, because there's difference of squares. So I set it up like this. F of x is equal to x minus 1 squared minus I squared. Then I still have times x plus 8. Multiplying this out, f of x is equal to x squared minus 2x plus 1. Then minus I squared is going to be plus 1. So still have to simplify in there, and then times by x plus 8. Now I have f of x is equal to x squared minus 2x plus 2 times x plus 8. Multiplying this out, f of x is equal to x to the third plus 8x squared minus 2x squared minus 16x plus 2x plus 16. So I'm running out of room. So I get for my polynomial x to the third plus 6x squared minus 14x plus 16, combining my like terms. Number 4, degree 4, zeros negative 1, 2, and 1 minus 2i. So I have negative 1, 2, 1 minus 2i, which then means I have 1 plus 2i. Now I have my 4 zeros. Set each of them equal to x. Once I have each of them equal to x, now I need to solve them so that they're equal to 0. For my first 0, add 1 to both sides, so I have x plus 1 equals 0. For the second one, I have x equals 2, so subtract 2 from both sides. I have x minus 2 equals 0. The next one, I have to subtract 1 and add 2i to both sides, so x minus 1 plus 2i equals 0. And then subtract 1 and subtract 2i. X minus 1 minus 2i equals 0. F of x is equal to x plus 1 times x minus 2 times x minus 1 plus 2i times x minus 1 minus 2i. First, multiply the first set of binomials together. X squared minus x minus 2. Then times, I'm going to go over here and do the same thing that I did before. So I'm going to get x minus 1 squared, which is x squared minus 2x plus 1. Then minus 4i squared, which means for this one, then I add 4. So I have f of x is equal to x squared minus x minus 2 times x squared minus 2x plus 5. Keep multiplying. So now I have to distribute. As I'm going to distribute here, I'm going to also write it in the vertical format. So f of x is equal to x to the 4th. So I'm distributing x squared to both terms, or excuse me, to all three terms. So I have x to the 4th minus 2x cubed plus 5x squared. Now I'm going to distribute my minus x to all three terms. So minus x to the 3rd plus 2x squared minus 5x. And then last, distribute my negative 2 to every term. So I have minus 2x squared plus 4x minus 10. Add them together, add my like terms together. So I get x to the 4th minus 3x to the 3rd plus 5x squared minus x minus 10. All right, let's talk about writing polynomials as products of linear factors. In some of these equations, you're going to be given 1, 0. If you're given 1, 0, then you can use your synthetic division and so forth, what I'm going to use. I went with the examples that I'm going to do are ones that no 0 is given to me. So what we're going to do, examples that we're going to look at are how to find complex zeros of the polynomial function. First thing, how many zeros are there? Number 2, factor the polynomial if possible. If a factor is quadratic that is not factorable, you're going to have to use the quadratic formula to figure out what the factors actually are. If not factorable and the degree is greater than 2, you must consider what are my possible factors. Then use synthetic division. Number 5, the directions, find all zeros of the function and write the polynomial as a product of linear factors. So here I have a 5-term polynomial. First of all, we're not talking about grouping or anything here with a 5-term polynomial. What I'm going to have to do, think about what are my potential zeros here. Remember, we did that in the last section. Potential zeros. For number 5, let's say if I'm using my remainder theorem, I'm going to try f of 1. 1 could be a possible factor. So I would have 1 to the 4th plus 4 times 1 to the 3rd plus 12 times 1 squared plus 36 times 1 plus 27. Well, f of 1 is equal to 80, which means 1 is not a factor of that polynomial. Now let's try f of negative 1. Negative 1 to the 4th plus 4 times negative 1 cubed plus 12 times negative 1 squared plus 36 times negative 1 plus 27. Well, f of negative 1 is equal to 0. Since f of negative 1 is equal to 0, then negative 1 is a factor. Now I'm going to use synthetic division and divide out negative 1. So negative 1, my coefficients 1, 4, 12, 36, and 27. Bring down my 1. Negative 1 times 1 is negative 1. Add, I get 3. Negative 1 times 3, I get negative 3. Add, I get 9. Multiply negative 1 times 9, negative 9. Add, I get 27. Negative 1 times 27, negative 27. Then I have 0. Since negative 1 is a 0, that means x equals negative 1, which x plus 1 is my factor. So x plus 1 is my first factor of my polynomial. And then what's left is x to the 3rd plus 3x squared plus 9x plus 27. That's what's left in my synthetic division. Now I have a 4-term polynomial. Can I factor this 4-term polynomial? Group the first 2, group the last 2. So I have f of x is equal to, I have this x plus 1 out in front. Well, then I have x squared, open my parentheses, x plus 3. What can I factor out of these two that I'll have an x plus 3 with a sign, positive 9. Open my parentheses, I'm left with x plus 3. Now I have f of x is equal to x plus 1 times x plus 3. Open my parentheses, I'm left with x squared plus 9. I have to keep going with this quadratic that's right here. In order for me to figure out what my factors are, I would have to set that equal to 0 and solve it. I would have x squared plus 9 equals 0. Subtract 9 from both sides, so I have x squared equals negative 9. Take the square root of both sides. Once I take the square root of both sides, I have a positive and a negative. So I have x is equal to positive and negative 3i. I'm writing my factors. This factor is fine. This factor is fine. Remember, when I have to write them as factors, they have to be set equal to 0. Once again, I have to go backwards. So that would mean I would have x plus 3i equals 0, and x minus 3i equals 0. So my factors in factored form is x plus 1 times x plus 3 times x minus 3i times x plus 3i. My degree is 4. I have 4 factors here. Number 6. Here I have a 4-term polynomial. If I try to factor by grouping here with a 4-term polynomial, when I factor out x squared from these first 2 terms, right, I'm left with x plus 6. Is there anything I can factor out of these last 2 terms that I'll be left with a positive x plus 6? No. So therefore, I can't factor it that way. Since I can't factor it by grouping, I'm just going to go through some potential zeros. I find that f of negative 2 equals 0. So once I find that negative 2, by plugging in negative 2 into that function and getting 0, then I know negative 2 is a 0. Now I'm going to use my synthetic division. Negative 2 1 coefficient, 6 coefficient, 13, then my constant 10. Bring down my 1. Negative 2 times 1, negative 2. Add 4. 4 times negative 2 is negative 8. Add 5. Negative 2 times 5 is negative 10. Add them together, I get 0. So my remainder is 0 because negative 2 is a 0. Since negative 2 is a 0, that means x plus 2 is a factor. Now I'm left with, for my polynomial, f of x is equal to x plus 2 times x squared plus 4x plus 5. Now I would need to factor this quadratic equation in here. Well, do I have factors of 5 that when they're both positive are going to add up to 4? No. I'm going to take this quadratic and set it equal to 0. Use my quadratic formula to solve it. X is equal to negative b plus minus the square root of b squared minus 4 times a times c, all divided by 2 times a. X is then equal to negative 4 plus minus the square root of negative 4 divided by 2. I have x is equal to negative 4 plus minus 2i divided by 2. My 2 zeros, I get x is equal to negative 2 plus minus I, which means I have x plus 2 minus I equals 0, and x plus 2 plus I equals 0. Now writing this function as a product of linear factors, I have x plus 2 times x plus 2 minus I times x plus 2 plus I.